So we talked about the schematic diagram and the symbols. Then we got into the resistances. Now, before I forget, we got a text back from the department secretary who checked over with the bookstore, and I sent out an email, I guess it was Friday or Saturday, that she had heard back from the bookstore, and apparently the textbooks are now accessible by you. So you should be able to, if you're a member of the or a part of the NCC Access program, you should be able to access the textbook. And if you, I think you had the option of buying the textbook for an additional sum to go from an e-version to a book, a hard paper version. But either way, you should be able to get the textbook. So I would advise you to do that, because I will start assigning homework now that the textbook is available. And if you haven't gotten it, shoot on over to the library virtually and figure out how to get to the ebook.
How do we access the textbook?
You're gonna have to check.
How are we supposed to access?
You got to check with the library not the library, the bookstore on that one. I'm not sure. This is the first time they're going through, so I have no idea how this works at all. But the bookstore should be able to tell you. If you did the NCC Access program, then they should be able to either send you a link or something to somehow get. I know it's an ebook version. I just don't know how you access it, but they should be able to do that. And you might have gotten an email too. Check your back emails, because I know that on some of the stuff when I've asked about it, Barbara, the secretary, has sent me, well, this was an email that was sent out or whatever. So check your back emails about the Access program, and it might have something in there.
I'll double check, but like for my last textbook, we also have a book that's there. I am opted into the program. When you put in like your NCC number for the bookstore, it will tell you like the courses that you have, and
Right.
it will show you what you need. For like one of my classes, when you scroll down, all I saw was the access code, so I was able to like get my book that way because there was an access code. But I checked just this morning for your class, and I didn't see anything differently. So
you're saying the access code isn't there?
no, not when I saw this morning. It might be different now, but I checked like at like 9.
That's surprising, because I thought she said they were ready. All right, let me make a note.
I can double check now too while I'm on the phone.
Okay, well, while you're checking that, so we talked about the resistance symbol, and I made myself a note to check on it too. We talked about the resistance symbol. We talked about the different kinds of resistors, that there were carbon composition resistors. We talked about the leaded components versus the leadless components. These are leadless components, considered to be leadless. These are, and we talked about the fact that these are not to scale, that in reality, this little chip resistor is smaller than the smallest of the carbon composition resistors. Then we talked about how, again, we could have a radial lead or an array. And we talked about that each of these might have multiple resistors in it. And then we talked about the construction of some of the resistors. Remember, all of these are out of the textbook. So when you get the textbook, you'll be able to look at them. How the chip resistors are constructed, and how the carbon composition resistor was constructed. And then we also talked about the film resistors and how they're made. Okay, so we had a whole bunch of different resistors. What I wanted to do very quickly, we talked about power resistors too, that the power resistors are much, much bigger. Again, these are not to scale, that this can be anywhere multiple inches long, that this one at 5 watts is probably about 2 inches long and maybe little over 1/2 inch by 1/2 inch. Professor Atwood went over the color code with you, so I believe, is that correct?
Mm-hmm.
All right, so I'm not going to spend time
Yep.
on that. Did he do the, he did the 3-band. Did he do the 5-band as well?
No.
Okay, 5-band works exactly the same as the 4-band, except it's got an extra band for a digit. So instead of first digit, second digit multiplier, it has first digit, second digit, third digit, and a multiplier and a tolerance band. So if I looked at this one, we have, I'm assuming this is red, shows up as pinkish on mine, but red, violet, black, yellow, or gold rather. So if we looked at this one, just to do one quick example of a 5-band resistor, let me change the pointer into a pen. So we've got, I'm going to just write the colors so that we're all on the same page. So this is red, yellow, black, gold. We know that there's only 9 colors, so you've got brown, black, black, brown, red, orange, yellow, green, blue, violet, gray, white. And for tolerance, we have gold and silver. The only reason I'm writing all of these out is if we have anything that's got colors on it that I'm going to do manually, I'm going to use a 2-digit abbreviation, 2-character abbreviation. So black is BK, brown is BR, red is RD, orange is OR, yellow is YW, green is GN, blue is BL, violet is VI, gray is GY, white is WH, gold is GD, and silver is SI. So those are the 2-letter abbreviations that I'll use for any of the colors. If I need to, if that, like in this one, in my opinion, that's very questionable what that first color is. So we've got it there ahead of time. So that may be not gold, that may be yellow, thinking about it, because it's not a multiplier.
Hey, Professor.
Yes.
You know how like for some resistors they are 4 bands, but they'll only show you the first 3 bands, and then they won't have a band for the last one, so you'll use like 20% as the tolerance.
Right.
Is it the same thing for the 5 bands? So will they have 4 bands but no 5th band, and then
No,
you use the tolerance of?
no, they'll always be, because remember, what we're doing is by adding that 3rd digit, we're getting more precision. So you wouldn't have a resistor that you're getting more precisions with, but it would almost be as if I could say to you, I'm going to charge $1. I'm going to charge $12 for something, but my increment is,
Mm-hmm.
my accuracy or my tolerance is plus or minus 50%. So that would be, it could be $12.50 down to $11.50. All right. It would make no sense to say, I'm going to charge $12 for something with a tolerance of plus or minus $5. or plus or minus $10.
Okay.
The tolerance wants to be small compared to the number. So if I've got 3 digits, the tolerance on a 5-band resistor are generally either going to be 2%, 1%, or 0.5%.
Mm.
Okay, so you'll never have a situation where the tolerance is going to be 20%. It just wouldn't make sense. You know, if I'm gonna tell you, if I'm gonna say to you, to the nearest dollar, the value is $12.37. Well, if I'm specifying $12.37, how am I going to specify that to the nearest dollar? The tolerance isn't there. So you're always going to have on a 5-band resistor, the ones usually are 2%, 1%, or 0.5%. Never 20%. Okay, so getting back to where we were, it's the same drill as when you did. We're going to write the first digit, so red is 2. We're going to write the second digit, which is yellow, which is 4. We're going to write the third digit, which is black, so there's no 0, 0, so it's a 0. And then the multiplier is yellow, which is 4. Oh, wait a minute. Oh, man. Cross that out.
Wait, that looks like gold for me.
Yeah, hold on. Wait a minute. It's me. Hold on. In the old days, that color used to be violet. So violet, the second band, is violet, not, I don't know what made me write yellow. It's violet. Violet is 7. The third band, it has to be a multiplier. So this is a 2. This is a 7. That's a 0. This is the multiplier. And this is the tolerance. That's why I put yellow up here, because you couldn't have, well, you could have. So is that gold or is that yellow? If I look at the one on the right, maybe the one on the right looks more
That
like
looks
yellow.
gold. That looks gold. That's yellow.
Yeah, okay. So if this is gold, if that is indeed gold, because I didn't look at the other resistors when we put it up. So if this is gold, gold means what? Did he go over that?
The tolerance is 5%.
No, God, that's a tolerance. In terms of value, did he talk about?
It's 0.1 multiplier.
Yeah, so gold means as a multiplier, it means divide by 10 or multiply by 0.1. If I had silver as a multiplier, it would be divide by 100. Okay, so now if we're dividing by 10, we're going to take that and put that there. So this is going to be exactly 27.0 ohms. Okay. So again, it's the same. If we look at, let's look at this one down on the bottom. We'll look at C. So this is
for the tolerance, excuse me, for the tolerance of the colors, it would be 0 or?
Of what?
Like,
The
you know, like
the tolerance.
the tolerance, yeah.
That would be red is the tolerance, and I'd have to double check because I don't use these that often. I want to say off the top of my head, it's going to be 2%, but I can't swear to that. I'd have to go back, and I don't want to go off this screen or I'm going to lose all my handwriting.
Oh, okay, okay. No.
All right. But we
Professor, I'm on the bookstore.
Yeah.
Oh, sorry.
Go ahead.
I'm on the bookstore. It doesn't say anything. All it says is section note, folio access. It says the same thing for Professor Atwood, but his says no books required for this course. Yours doesn't say anything.
All right, I'll have them check into it again.
Okay. You want me to send you like a screenshot or anything?
Yeah, if you could, that would be great.
Okay. I'll send it to you today.
Okay, thank you. So I'm thinking that maybe that's 2%, but again, we'd have to double check that. And so if we look at this one, we have first digit is a 3, second digit is a 3, the third digit is red, which is a 2, and the multiplier is orange, so that would be 3 zeros. So that would be 332,000 ohms, which we know is the same as 332 k ohms. And the tolerance here is green. And if I had to guess, I'm going to guess that it's 0.5%. But I can't swear to that. We could double check it. But it's the same drill, whether it's a 4-band or a 5-band resistor. The only difference is how many digits you write down before you start moving the decimal point. Okay?
So the 4-band, actually, the multiplier goes down one color. For 330 ohms, for example, in 2 bands, in 3 bands, I will have red, and brown.
330 would be orange, brown. 220
3?
would be red, brown. But yeah, so what it is, so the first, these are digits. The next band is a multiplier. If I had a 2-band, let me do that up here, a 4-band, I would have I would have 2 digits, a multiplier, and tolerance. Right? So it's just a matter of, are there 2 digits or are there 3 digits before you start worrying about the multiplier? In a 5-band, it's going to be 3 digits. In a 4-band, it's going to be 2 digits. Okay. Homework assignment tied into this. After a while, you know, right now, you're going to sit there and do what we did, saying, okay, first band's red, second band's violet, third band's brown, whatever. And you're going to write them down and you're going to figure it out. After a while, after you work for a while, you're just going to look at a resistor and go, it's 22K. Or you're going to look at a resistor and go, it's 4,700 ohms. Or you're going to look at a resistor and go, it's 560 ohms. Part of that is because you've worked with it a while. Part of it is the fact that there are only 24 what we call 5% standard values. So this ties back to the 3-band model. Okay? If I think about the 3-band model, there are 24 standard, or sometimes called preferred, values. Okay, so this is for 5%. All right, so 10 is one of them, 11 is one of them, 12 is the next, and so on, all the way down. So there's 24 of those. That'll always be these first 2 bands. in a three, where the value is determined by three bands, a 4-band color band resistor value. There's only 24 of those values, and after a while, you get to know them. I see a 2 and a violet. I mean, I see a red and a violet, and I immediately know it's 27. I don't think about it individually. And then it's just a matter of you look at the third band to say, where do I put the zeros? So if I see a red, if I see red, violet, red, I know it's 27 followed by 2 zeros or 2.7 k ohms. That just becomes second nature. So the homework is make a list of the 24 standard %5 resistor values from 10 ohms to 99 ohms. Due on Thursday. So you're going to have, if you think about those first two digits, what's the difference between 10, 100, 1,000, 10,000, or what's the difference between 39 ohms, 390 ohms, 3,900 ohms, 39,000 ohms? What stays the same? What changes?
The color of the third band.
The color of the third band changes, right?
Yeah.
So if you think about all of these, the first band and the second
Black.
band. I have on my pen that I use with my tablet, there's a little clicker. And when you click it by accident, the whole page goes away.
There might be a button that say undo. Maybe you can do
No,
that.
I tried that when it happened to me this morning. I tried reset, I tried Control Z, I tried undo. It makes it go away. Something with my tablet. I have to see if there's a way in my tablet software of disabling the clicker that's on the pen. All right, anyway, so if we think about it, that digit stays the same and that digit stays the same. So for all of these, if I looked at this, this would be brown, black,
Black
something.
and black. And that's a black too.
Well, for all of them, this would be brown, black, black. This would be brown, black, brown, brown, black, red, brown, black, orange. But the first ones are always brown and black.
Oh, yeah.
All right, it's brown, black, followed by something. If I thought about 39, 390, 3,900, these are all orange, gray, followed by something.
It's white.
Yes, it's white. Thank you. Gray is 8.
So for homework, we're just going to be doing that and like from 10 all the way down to 99.
Hold on one second. Let me just get me back where I am.
All right, no problem.
So you're not doing all of this. All you're doing is giving me a list. And I said to you before, the list starts as 10, goes to 11, goes to 12, and you're going to figure out the rest. And I'll tell you that the last one is 91. So there should be, all in total, 24 of these.
Okay.
Because now if I took 1, 2, I could make it 12 ohms. I could make it 120, 1200, 12,000, 1.2,
Ah, okay, okay,
all right, by what I put as the multiplier.
okay.
Okay. So if you know those 24 values, and they're going to be important. I do this in a lot of my classes because like in the ELT203 class, we do a lot of designing a circuit. And what you're going to do is you're going to pick the nearest standard value to put in your design rather than stringing 3 resistors to get exactly what you wanted. You always go with the nearest standard values. It helps to know what the nearest standard values are. Just coincidentally, so these are 5% values. If I wanted the 10% tolerances, it would be every other 5% value. So 10% tolerance, the preferred value is 10, the next preferred value is 12. So when you get that list of 24 for 5%, starting with 10, every other one is a 10% value.
Does that mean that there are only 12 standard preferred values?
12
for
preferred
10%?
values for 24.
Sorry?
Okay? All right, so
Can you
let's keep
repeat
going.
that? So does that mean that there are only 12 values for 10%?
Yes, there are only 12 values for 10% and only 6 values,
Okay.
6 values for 20%.
Okay.
Okay. So everybody know what they're doing for homework? You're finding those
Yeah.
24 values, 5% preferred values or standard values, and just give me a list of 10, 11, 12, and so on. Okay. Okay. Oh, some resistors will be labeled, the chip resistors in particular, will be labeled with an actual printout. Rather than put colors on those tiny things, they actually print letters and numbers. And what they do is, let me go back to a pointer so I can point. So what they do is, you might see something like, let's do this one, 2M2. So the letter serves as the decimal point. So this would be 2.2. The question is 2.2 what? Well, the letter tells you what, 2.2 mega ohms. If it's less, a smaller value, then it might have 22 with an R after it. The R says ohms. 220K ohms. Okay. So you might see something like, just see. You might see something on a resistor that looks like 4K7. So what would that be?
4007.
4007? Like 4007?
Yeah.
Okay, maybe. Remember, this middle guy here is going to serve 2 functions. It's going to serve as where the decimal point is.
So it's 4000.7.
There we go. And then it's also going to serve as the multiplier. So what we would write is, we would write 4.7. And so that's telling us the decimal points between the 4 and the 7. The multiplier is telling you it's in K ohms. So this is going to be 4.7 K ohms. Okay. So when you see that, that's the format that it uses. Okay. All of these resistors we've used so far, let me switch screens here. Everybody got that so I can switch out of it?
Professor,
Yeah.
for that last example that you had, where it was 0.1 ohms and then it was like 0 R1,
Yeah.
is the R standing for red here, or what is the
Oh,
R
it's just,
for?
you couldn't, if I said to you, what would you call an abbreviation for ohms? What would you say? Probably O. Well, you can't use an O because it looks too close to a 0. So I guess they used an R because it's a resistor, but the R in this case, if we looked at this, this would be saying that the decimal point is between the 0 and the 1, and it's in ohms. So if you have an R there, the value is in ohms, as opposed to meg or as opposed to K.
Okay, so it's just kind of like a placeholder type thing.
It again, whenever you have a letter in one of these, it always does two things. It tells you the decimal point, where the decimal point is, and what the multiplier is. So in this one, it's saying that the decimal point is to the right of the second two. And since it's not K or meg, it's in ohms. The R is for ohms. This one over here said that this is in meg. Did I lose my, oh, when I stopped sharing that? Hold on, let me put that screen
Yeah.
back.
All right.
So this one is saying that the decimal point is to the right of the 2. And because it's an R, it's in ohms. So that was 22 ohms. This is saying the
Okay.
decimal point is between the two twos. So it's 2.2 something. And the something is megohms. This one down here is saying the decimal point is between the 0 and the 1. So it's 0.1 something. And the something is ohms. All right, makes sense? Yes, no?
Yes.
Okay. All right, so let me see if I can get back to my whiteboard. Where was I going with that? No, that's in Zoom. Just give me a second to bring up. Okay, now I can share that. Okay. So all of those resistors we've talked about are fixed value resistors. And as the name implies, fixed value means that the value does not change. There are also what we call variable resistors. And these are designed to allow the value or the resistance to change. If we think about variable resistors, now this may be a stretch for some of you, but back in the olden days, we actually had to turn a knob to change the volume of a radio or a television. Imagine that. No button, a knob we had to turn. That knob was connected to a variable resistor. Okay. If we think about a fixed resistor, so I've got a wire, and between the two ends, the two wires, I've got resistive material. Well, if I took a meter that measures resistance, called an ohm meter, if I took a resistor, an ohm meter, and measured from this wire to this wire, and let's say it read 500 ohms, and I measured it again, it would again read 500 ohms. And if I measured it again, it would again read 500 ohms, assuming that the temperature doesn't make the value change or whatever. But if I kept reading it, it would be the same value. Well, what would happen if instead of that, I had a way of making a contact that made contact with the resistive material here and brought out a wire there? Now, when I took my meter, my ohm meter, and connected between this point and this point, I'd only be measuring the resistance of that amount of resistive material. So what do you think would happen to my measurement? If my initial measurement end to end was 500, what do you think would happen to my measurement now?
Would it get cut in
All
half?
the same.
Would it get cut in half?
Say again?
Would it be cut in half?
Well, maybe. Bottom line is it would go down, right? And I'll talk more about whether it's in half or not in a minute. So now what I've got is I've got a smaller value resistor. But what about instead of that, what about if I took it and I made that contact move over to there? Now, what's going to happen? Now I'm measuring the amount of resistive material between this point and this point.
It would increase?
And it would increase. So what have I done? By moving this contact back and forth, I can make the resistance that I measure change. Okay? This contact that moves back and forth is sometimes called the wiper. And if I move the wiper back and forth, I can change the amount of resistance I get from the wiper to one end. Just out of curiosity, somebody told me when you move the wiper from here to here, the resistance goes up. But what about if I was measuring from the wiper to the other end? What would happen when I moved the wiper from here to here? Go up, go down, or stay the same? Any ideas?
Go down.
It would go down. Before, I was measuring the amount of resistive material from the wire to the wiper. When I move the wiper to the new position, now I'm only measuring the amount of resistive material from here to here, which is less resistive material. So the value measured to this end, the right end, as I moved from first position to second position would go down, while the measurement from the left end to the wiper would go up. Okay. So that would mean that I can change the resistance. I can make the resistance go up, or I can make the resistance go down, depending on whether I measure from the wiper to one end or the wiper to the other end. Now, somebody said to me, would the resistance go down in half? And I said I would get back to that. There are two, well, let's go this first. There's something called the taper. And the taper is how the resistance changes when the wiper is moved. Okay. One of the type is called a linear taper. And it's just what the name implies. If I move the wiper halfway, I've got half the resistance of the total. So if it's 1,000 ohms end to end, and I move the wiper to the middle, I've got 500 ohms. If I move the wiper 3/4 of the way, I've got 750 ohms. If I move the wiper 1/10 of the way, I've got 100 ohms. It's linear. Okay. The second type is called an audio taper or a logarithmic taper. And these are nonlinear. And I'm not going to take time to go into how they're different. You should just be aware of the fact that you can buy variable resistors that are linear. So if I move my wiper halfway, I get half the resistance. Or I can get them in a nonlinear, which if I move it halfway, doesn't give me half the resistance. Okay, so you should be aware of the fact that there are linear taper and audio or logarithmic taper variable resistors. So how do we physically make that? How do we make that happen? There's a couple of different ways. If I envision that I take my resistive material and bend it into a circle, that's supposed to be pretty much a circle, and I bring out a wire on each end. Right now, with exactly what I've drawn, have I got a variable or fixed value resistor? This is one wire coming out. This is the other wire coming out. Variable or fixed value? Somebody take a guess.
Fixed.
Fixed value. It's a fixed value resistor. The only place I can measure to is from this end to this end. But what I can do is put a wiper on. And the wiper connects to a shaft. And usually on the shaft, you can put a knob to turn it and whatever. And we also bring a wire out that's connected to the shaft, which is connected to the wiper. So this is a shaft. To rotate the wiper. This is, of course, the wiper. And what I labeled as 1 are the contacts, or the wires that we can make connection to. Now I could take the wiper and I could move it over to here. And now I'm just measuring this much resistance. If I turn the wiper so it's in the position where I've shown it here, I'm measuring the resistance of all of this resistive material, and we've got more resistance. If I move the wiper to here, now I'm measuring the resistance from here, all of this material to here before we get out to the wiper contact. So by turning the shaft, I can move the wiper from here to here to here or anywhere in between and change the amount of resistance I would have between one end and the wiper. If I measure end to end, I'm always going to get the same value. When I measure from the wiper to one end or the other, as I turn the shaft and turn the wiper, it's going to change the resistance value. Is this making sense? Yes? No?
Yep.
Yeah.
Yeah.
Okay. The other way you can do this is you can take out the resistive element. Let me make that level. Oops. So there's your resistive element. Still have a wire connected to one end. Still have a wire connected to the other end. And now what we can do is we can make the wiper a contact that comes out like that. And we connect a wire to the wiper that comes out on its own. And now this is one end, this is the other. If the wiper's where it is, I'm measuring the resistance of this much. If I slide the wiper over to here, it makes contact. I'm measuring the resistance from here, all of this resistance material back out to here and around. So I can change it that way. If you've ever seen anything that's got a slide pot on it, when you slide that slider up and down, what you're doing is you're moving where the wiper makes contact on the resistance in the whatever it is you're using. They can take this design and move it to the next step. Same idea. Same idea with the wiper. Except instead of attaching a knob to the top of the wiper, what they do is put a screw there. So this is a screw. It's got screw threads on it. Now, normally, if I took a screw and turned the screw goes into the material. But what happens if I lock the screw in position and turned it. Well, then what would happen is instead of the screw turning, the screw moving, the screw would stay where it was, and the material that it's screwing into would move back and forth. So what they do is they put a lock. There's a notch in the screw that goes all the way around. This is a lock. So this prevents the screw from moving back and forth. So if I lock this so the screw can't move back and forth, then what has to happen is this has to, as I turn the screw, that's going to make the wiper move back and forth. So this is a captivated screw. This is the wiper, and turning the screw moves the wiper back and forth. Most of these are what we call potentiometers. All right. So all of these, whether I look at it this way or this way, these are generally called potentiometers. There is another type of ways of using a variable resistor called a rheostat. But the way we've drawn these using all three leads is called a potentiometer. Now, potentiometer we usually shorthand to pot. So this is sometimes called a trim pot. And the way this works is how many times you have to turn the screw will tell you what kind of pot it is. So there are 10-turn trim pots, 20-turn trim pots. A 10-turn trim pot says you have to turn this screw 10 revolutions to move the wiper from one end to the other. A 20-turn trim pot says you got to move the screw head through 20 revolutions to get the wiper to move from one end to the other. Either of these allow you to make a very, very fine adjustment about where the wiper is in terms of its position. A 20-turn pot, you turn it one turn, you've moved 1/20th of this distance. If I move it a half a turn, I've moved 1/40th of the distance. A quarter of the turn, I've moved 1/80th of the distance. So you can get a very, very fine adjustment of the pot. You could get a much, much finer increment on one of these than you could on one of these. If I said to you, all right, let's assume it's a linear pot. Let's say it's 1,000 ohms. If it's a 20-turn pot, each revolution is 50 ohms. That means that a half a revolution is 25 ohms. A quarter of a revolution is 12.5 ohms. So if I rotate this a quarter of a turn, I've changed the resistance from the wiper to one end by 12.5 ohms. There's no way you could adjust one of these to see a 12.5 ohm change. Guarantee by the time you start to move, you've already gone past 12.5 ohms. So these are used for precise adjustments, the trim pots. These are used for general purpose. Okay, questions? Anybody need more time to jot down notes before I leave this one? Okay. Trim pots get to be used a lot. They teach you a lot of things too. I learned about caffeine and coffee through a trim pot. When I was working, my standard procedure would be in the morning, I would get my cup of coffee and I would look at the worksheets of what had to get done. And I'd sit there and have my cup of coffee while I was saying, okay, I'm going to do this, then I'm going to do that, then figure out what I was doing for the day. One day I went down to the coffee shop. They didn't have the small coffee, but she said, I'll give you a large size coffee for the same price. I said, okay, can't beat that. And I went and in my normal 10 minutes or so, instead of having my small cup of coffee, I had my El Grande cup of coffee. And about an hour later, I went to adjust something in a trim pot. These are very, very small heads. This head here, this diameter is less than a quarter of an inch. So is the slot small. So I've got my large grande size coffee and I'm like trying to put my hand into the slot while my hand is shaking from the caffeine overdose that I was going through. It was like, yeah, okay. We learned a lesson on that one. But trim pots are in a lot of places. Okay.
What if you take the round potentiometer and on the shaft you put a large gear and then connect it to a small gear with the knob?
Yeah, well, that would work. That was done a lot, that kind of thing. Not so much with resistors. I've seen it done with resistors. But a lot of times on radios, on tuning capacitors, they would do that. Either gear it down with a gear or gear it down with a pulley situation and a string that they would gear it down. You could do that, and that would certainly accomplish the same thing. But the whole thing is you're trying to, make one revolution of whether it's this, or some knob over here which changes this. Make that one revolution be a very small amount of resistance change. Yeah, that would work. And like I said, I have seen it done on pots, but more so on tuning capacitors in radios. Okay. Let's see where we were at. Let me just see if there's anything on here that I wanted to hit on the. Oh. Let me share this very briefly. Okay, so this is what a typical round pot would look like. There's 3 lugs. Most of the time, the middle lug is the wiper, and these are the 2 ends. All right, so they would correspond to what we saw before. This is what that trim pot I was just talking about. So this whole thing is maybe 1.5 inches long, little over a quarter of an inch wide, maybe 3/8, a little over a quarter, maybe 3/8 of an inch high. So this slot's not that big. And again, what's inside is what we just described. So if you look at the next one, whoops, here's that screw I was talking about. The screw is captivated, so it can't move. So when you turn the screw, this is what has to move, and that's where your wiper contact is. You also see them trim pots this way, and this is almost that gearing that you were just talking about, Ronnie, in that kind of an idea. And with this, we talked about that. We talked about. All right. We only have 8 minutes left, so I might as well talk about other kinds of variable resistors, and then we'll talk about, starting next on Thursday, we'll talk about the simple electric circuit. There are other types of variable resistors. These are variable resistors that we use as sensors. So a thermistor, A thermistor measures temperature. When we talk about thermistors, you'll see PTC and NTC. PTC is positive temperature coefficient. What that means as the temperature goes up, the resistance goes up. NTC stands for negative temperature coefficient, which means as the temperature goes up, the resistance goes down. So a thermistor is a variable resistor, but instead of us controlling it, the temperature controls it. A photoconductive cell measures light. Most photoconductive cells, the more light that hits it, the lower the resistance. So as the light goes up, it gets brighter, the resistance goes down. Now, to talk about a strain gauge, let's talk about resistance. Damn. Did everybody get that stuff? I hit the button on my, I really have to go in and shut that off. The resistance of a material is given by the formula rho L over A. So if I think I've got a block, so here's some material, carbon, steel, copper, whatever. This is the cross-sectional area. Which in the formula is A. This is the length of the material. And rho is the coefficient of resistance. So that's dependent on the material. So let me ask you a question. Looking at this formula, if I make L increase, what happens to my resistance? Gets bigger, smaller, stays the same.
It will also get bigger.
If we increase the length, the resistance
Yes,
goes
lower.
up. Okay. What about if I increase the area? What happens to my resistance?
That gets lower.
That gets smaller. So let me think about this for a minute. So if I take this piece of copper, let's say, and I stretch it so that it's that long, what's going to happen to the cross-sectional area, do you think? Think about if you took a rubber band and stretched the rubber band. What happens to the width and the height of the rubber band as you stretch it?
It also stretch.
Gets bigger or smaller?
It's bigger.
Not length, not the long way. I don't have a rubber band in front of me.
It gets smaller because you're stretching it out, so it's less thicker. It becomes thin.
Yeah, if I stretch a rubber band out and I measured the thickness of the rubber band and the width of the rubber band, when I stretched it, that height's going to get smaller, the thickness is going to get smaller, and the width is going to get smaller. That means the cross-sectional area gets smaller. So wait a minute. We just stretched it, which made the length longer, which we just figured out makes the resistance go up. And we made the area smaller. So if I make the area smaller, the resistance also goes up. So if I took this piece of copper I've got sitting over here, if I took this piece of copper I've got sitting over here, I just want to make sure I still had you on the screen, and stretch it, stretching it makes the length get bigger, makes the area get smaller, and both of those make the resistance go up. That's the whole principle behind a strain gauge. What we do with a strain gauge is we take a resistive material and we lay it, usually in this kind of format, on some what we call a substrate. The substrate is flexible. Then what happens is we put this and glue it to whatever we want to measure the force on. So we glue it, and what we do is we're going to stretch it this way. Stretching it this way is going to do to each one of these runs that go this way, it's going to do what it did down here. Make the length longer, make the area smaller, which is going to make the resistance increase. So as I stretch this or let it come back to where it was and stretch it out again and come back to where it was, that is a function of the resistance, or it's going to make the resistance change. Turns out that the force on whatever this is glued to is making that happen. So a lot of times when they'll test, let's say an airplane wing, they'll glue these all over the wing at various points in the wing and hook it up to a computer. And then they'll set the wing into a wind tunnel. And they can see which part of the wings stretch and which part of the wings compress, all by reading the change in resistance of the strain gauge. Okay? Strain gauges are used in cars. If I take this strain gauge and glue it to a cylindrical piece of, let's say, aluminum, that creates what's called a load cell. Now, airbags are good?
Yes.
In a car? Yeah. And there's never been an injury in an airbag, right? Not so much.
Mm-hmm.
The problem was initially when they put airbags in cars, what they figured out pretty quickly was that if my airbag went off and hit me, and that same airbag went off and hit my wife, who's 5 foot and 100 pounds, that's going to have a much, much bigger impact on her than it is on me. So what they've actually done, they did two things with strain gauges and load cells. Number one, in a car today, if you get in and look at the dashboard, if you're the only one sitting in the car, usually you'll see on the dashboard a little indicator that the passenger airbag is not activated. How do they know that? There's nobody sitting in the seat. How do they know that? Because there's a strain gauge attached to a load cell somewhere that has not been compressed because nobody sat on it. So that's the first thing I do with strain gauge. The second thing is now they've actually gotten to the point where they've developed systems where the strain gauge will measure the passenger's weight and say, okay, based on that weight, we're going to adjust how fast the airbag deploys. So that if somebody small is in the car, it's not going to deploy as fast as if you had somebody larger in the car that you need more force to stop them from hitting the windshield. All of that happens because of variable resistors, because of strain gauges.
Wow.
Okay. We good?
Wow.
Questions?
Yeah.
Okay, I'll let you go because I just realized it's 20 after. So if you haven't gotten the textbook, get the textbook. I will again reach out to the department secretary, tell her what you told me. Natasha, did you send a screen capture to my screen, my email, perchance?
I'll send it to you today before 2 p.m.
Okay, if you can do that, that would be great. And then I'll send a copy to the department secretary to say, here's what my students are finding.
Okay.
Okay. All right. Thank you. See you all on Thursday. Have a
All right,
good
goodbye.
You too.
Bye.
Have a good day.